logging in. Someone's. Yeah. So there's no.
People can hear you.
Okay, perfect.
I guess we just start. So it's my pleasure to introduce the speaker today, Laura Mukasey. Laura Mukasey, sorry about that. Yeah, a little bit background information. So she got her PhD in 2017. It's actually joint supervisions from two universities. One is Seville University in Spain. The other one is Padova University in Italy. Then she started a postdoc position at Brazil University between 2017 and 2020, and then went to Surrey University and since then as a postdoc. And today she's going to talk about interplay of different reaction channels in low energy nuclear reactions with developed nuclear.
Thank you.
Yeah.
I'm very happy to be here with you today. So let's start. Yes, so I'm Laura Moschini from Surrey. And yeah, we talk about the interplay of reaction channels in low energy reactions with exotic nuclei. And it doesn't work. Okay. Yes, perfect. Okay, sorry about that. Okay, so a problem nowadays in theoretical nuclear physics is the simultaneous description of reaction channels in low energy processes with exotic nuclei. These kinds of reactions are involved, for example, in elements creation in the universe and are measured experimentally with ISO technique. For example, here at 3. And yeah, to be able to describe simultaneously all reaction channels will make us able to know the full reaction pathway. And this is interesting when planning an experiment, because it will allow us to predict if the process we want to study interferes with other processes and with other reaction channels. I am working on a new reaction model that aims, in fact, on tracing the interplay of different reaction channels and to provide the full pathway. This model is based on a time-dependent dynamics and on a molecular description of the structure. So during this seminar, I will show you all the steps and the insights that brought me to formulate this model. But first, let me give some context, because I've mentioned exotic nuclei, I've mentioned reaction channels, low energy processes. So let's see what do I mean with these concepts. Okay, so let's start with the nuclear chart. You know, of course, this represents possible isotopes. We have proton numbers that identify the elements, a neutron number that identifies the isotopes. In black here, we have the almost about 300 stable nuclei. And if we go far from the stability valley, we reach the edges of this chart where exotic nuclei sit. So if we zoom on the light mass region, again, we have here in gray the stable isotopes. And on the edges, we can find exotic nuclei. Here, I will talk about a particular kind that are halonuclei. Halonuclei are proton or neutron-rich nuclei. They present a low separation energy. This means that to remove one neutron or one proton, we need really low energy, about 1 MeV or less. And so they present an interesting structure. because you can describe them as a compact core plus one neutron or a proton or a couple of neutrons orbiting far away from this core. And this is forming the halo. Yeah, and then they are also short, they have a short half-life, so they decay in seconds or less. Here I will concentrate on one neutron halo nuclei. Example could be beryllium-11 or carbon-15. Beryllium-11 has, for example, a beryllium-10 core plus one neutron orbiting in the halo. So when this kind of nuclei interact with an heavy target, that could be a lead-208, for example, we can observe different outcomes. So we have our halo nucleus here with its core and the neutron impinging on a target. We can observe direct reactions or the formation of a compound nucleus. In direct reactions, it can happen that the neutron is still bound to the core at the end. This is in its initial condition or maybe in an excited state. This is an elastic or inelastic scattering. Or this neutron may be transferred to the other component of this reaction. And in fact, this is a transfer reaction. Or this neutron can break up and can be found free in the continuum, not bound to nor to the core or to the target. On the other side, these two objects can merge, so they lose their identity. We say they fuse together, and we would observe the emission and evaporation of gamma rays or particles. So we have powerful codes, powerful model that can describe the cross-section and can calculate the cross-section for all of these reaction channels. So let's take this case. Our traditional model will take the spectrum of our core. If we want to call it a beryllium-11, so it will mean to take the spectrum of a beryllium-10 and the spectrum of the other target, a lead, for example, like I said. And yeah, so they will define this spectrum asymptotically. And to describe each channel, we'll mean to assume our neutron is sitting in an initial state and to calculate a transition from this state to another one. For example, another bound state in this core spectrum would give us information on inelastic scattering. Transition from this initial state to the continuum of this nucleus will give us an idea of breakup, but we can also calculate multi-step transitions, and we can also end up to a state of the other nucleus, right? So this would be transferred, for example. The idea is that all the states included in this calculation are part of each of the spectrum of each individual nucleus. And these spectra are calculated when the two nuclei are far away, so asymptotically. And this, I repeat, this works particularly well, but when one channel is dominant. So sometimes channels may interfere. So let's see which situation would it be. So we have these two objects colliding, and we know that they feel an attractive nuclear interaction and a repulsive Coulomb interaction. This means that there will be this total interaction, this black line. And you see in particular, there is a barrier here, and we call it Coulomb barrier. So we know that, yeah, I'm not assuming angles now, so this is head-on collision. Reactions that occur at an energy above this Coulomb barrier will bring us to fusion, most likely in this case. Reactions that occur at energy below this barrier may end up in fusion, but we should overcome and tunnel this barrier. So fusion is less likely, and other channels are more likely to be populated. What happens when we are around this energy? Well, channel compete. So these are the low energy processes I mentioned in the beginning. And this happen at about or less than of MeV per nucleon. And what happens when channels compete? So there are measurements like this. Here we have a reaction between an helium-8 and gold. And they have measured the total cross-sections of the total fusion cross-sections, sorry, this is the red dots here. And they have observed that above the Coulomb barrier energy that is here indicated by this arrow, there is a suppression respect to a fusion calculation. A fusion calculation would be this dashed line, black dashed line, or black dotted line. And they also observe some enhancement below the Coulomb barrier. This is just an example. There are other reactions involving exotic nuclei that behave in this way. And they say that this effect, this suppression is due to the presence of other channels, in this case, transfer that they also measured and they plotted here. And they explain this saying that the probability, the tunnel probability, so the probability for this nuclei to fuse is dependent and sensitive on the shape of this of the two nuclei, which is changing during the reaction. So there's something happening during the reaction that changes the shape and the configuration of these nuclei, which is leading to this suppression. And this is due to the interplay of different channels. So what happens? That's when we plan experiments, we may think we will observe something because theory tells us you will see this result, but then you measure something different. And the opposite. I will take some data and then we'll expect to reproduce it with a calculation, and it's not happening, right? So yeah, this is why we need to study the interplay of different channels. And this is what led me to the first insight. So my first insight was I want to study the interplay of channels. This happens during the reaction, so I need to follow the entire reaction. I need a time-dependent model. And so basically we need to watch the reaction movie. So watching movie is fun. So let's start with this one. Nuclear reaction, a Star Wars story. So we have a beam of particles impinging on a target. These are our initial conditions. And the final observation is breakup, right? But then if we sit down and watch the movie, if we watch this reaction movie, we can find that this breakup has been induced by transfer. And it's not the end of the story, because this reaction happened in a laser environment. So we can learn interesting thing watching the entire movie. Let's watch a different one now, the wave function time evolution. So let's come back to our 1 neutron halonucleus impinging on a target. And let me show you this time-dependent model. Here we have as a scale Fermi for a special scale, 10 to the minus 15 meters. Time here really fast. We are talking about femtoseconds, and energies involved are MeV. So here we have two potential wells. Each one represents one nucleus. Sorry. So you know that if we take this potential well and we solve the eigenvalue eigenvector problem, we will get some bound states. And in fact, we can repeat this for the other potential, and we have some bound states. So let's assume that our neutron is sitting on this state. This is our initial situation. So we can calculate the wave function of this state. This will be the wave function of the neutron. This is a squared value. And yes, and define that this is our initial wave function. And we can solve the time-dependent Schrödinger equation. This is a semi-classical model. This means that the motion of this potential well during the time evolution is fixed by a classical trajectory. And yeah, so we have the same situation here, a projector that is impinging on this target with our initial wave function. We run the time evolution, and at intermediate time, things changed. So here we have the two potentials that have overlapped, and the configuration of the wave function of this total wave function is different. So here we have this blob here. That means that there's some probability to find at this point the neutron still bound to the initial state. But then there are two peaks here, and we can already see from this plot that there's some probability for this neutron to have transferred to the other potential, like in the Star Wars movie. And then at the end, this potential is going away, is traveling away, and we get the final wave function, total wave function. And this will give us the full pathway, the probability for any reaction channel. So in this case, we will have certain probability for an elastic scattering, certain probability for a transfer, and certain probability for a breakup, like in our movie. And this is only part of the story because this is the total wave function. But I want to study the interplay of channels, so I need to define channels in this reaction. And yeah, so let's do that. Let's come back to our potential. So let's solve again this eigenvalue eigenvector problems. Yes, we have some bound states, but we also have a continuum. This means that all positive energies are a solution of this equation, and all of them are associated to a wave that is oscillating until plus and minus infinity, right? And this is not really an easy object to deal in a computer code. So we need to discretize this continuum. There are several methods. We can, for example, apply an infinite waltz at some point in space. And this will provide us with a set of discretized states. And these states are normalizable. This means that they oscillate like continuum waves, but then at some point where we locate this wall, for example, the tail will go to zero exponentially. And so we can normalize it, we can include them in a computer code. But, yeah, of course, I'm talking about continuum because of course we want to describe all channels, breakup included. So if we want breakup, we need continuum, that's essential. And we have two wells. two potential worlds. So we have two sets of states here. We can play with it, we can change parameters here, we can remove one of them and keep only one set of continuum. We can just play and and run the same exercise as before. So we have this potential that is moving, following in a semi-classical way, so following a fixed trajectory. And now, instead of describing evolution of the total wave function, we define it as a superposition of these states, and we follow the evolution of the coefficients that regulate this superposition, and the coefficients carry the information of the probability to populate each state. Yes?
So if you include the two basis states, don't you end up with an overcomplete basis? And
that's a spoiler. That's a spoiler. Yes, yes. I will talk about that in a minute. Okay, so we can play with it in using different continuum configuration, and we can run and follow the evolution of these coefficients. And we get plots like this. So here we have the probability of the different channels. So elastic, transfer to the ground state of the other potential, transfer to the first excited state of the other potential, and breakup as a function of time. So the solid line are the results obtained by our benchmark calculation, that is the time evolution of the total wave function, and the dotted lines are the result of a certain calculation with a certain configuration. So this may work nicer or less nice, depending on which parameters and which initial condition we set. But anyway, we end up with something like this. For example, here breakup was really well described, and there were some problems with this transfer and also with elastic. But I want you to notice something here. So 0 times 0 is the turning point. This means that it's when the two potentials are close, the closest position. And if you sum up the probability at this time for the total wave function, it will give 1, which is physical, that's what expected, but you see, of course, that the dotted line will exceed 1. So yes, there's a problem here. But I really want to know what happens at intermediate state, because that's my goal, to see the interplay of these channels during the reaction. So I need to overcome this problem. And why this model failed at intermediate time? Well, because I fixed the basis asymptotically. I took the two potentials. I said, this is the spectrum, this is the other spectrum. And then I didn't consider that this is not valid at intermediate times. And yes, there's the problem that Philomena mentioned, that is each basis is complete, but then they are not orthogonal one respect to the other. So when they overlap, of course, the total probability will be the 1. I mean, we cannot trust what happens here because this is not physical. And this is something that, we can only trust what happens, the response at final time, so asymptotically. And this is what happens usually with the time-dependent models, that we can trust the final results, but during the reaction, it depends on how the model has been designed, but usually we may not trust what happens at the intermediate time. So I want to overcome that. And this is when I got the second insight. So it is good to use a time-dependent model, but I have to consider that the structure is changing. And so I have to use a different description of the structure. And that's why I decided to use the molecular structure, so a molecular model. So nuclear molecules come from actually atomic physics. Molecules in atomic physics are well-established objects, and there's a well-established theory. And then they have been applied to nuclear physics to describe mainly bound states and small particle bound states, and they have been used in time-independent models, except one case actually, but still with bound states. And you see there's a long history from the Frankfurt group. But yeah, what happens in a molecular model? In a molecular model, I consider that the core and the target are the two components of a molecule, and the distance between these two nuclei, these two components of the molecule, is changing during the reaction. So it's reducing and then it's increasing. And following this, the variation of the structure of this molecule, we are able to describe the structure that is changing during the reaction. And a consequence of this variation of the structure is the so-called Landau-Zener effect. So let me show you. And this is what brings interference, and this is why we can measure something different than what a model predicts. So let's take the spectrum of the two nuclei independently, asymptotically. And so here, the transition from one state to another has, there's some value, there's some energy gap there. Now, when we switch to molecular or two-centered spectrum, we have different spectra. So at large distance, when the molecule is initially defined, so when the distance between the two nuclei is really large, we have exactly the same situation as we had in this case. So here I have superposed the two spectra. And in fact, the transition between these two states is exactly what we can expect. But then at intermediate distance, the shape of this molecule changes and the spectrum changes. So this transition may be different. This is the Landau-Zener effect, and this is why the interference and all of those things happen. Let's look at something more quantitative now. So let's consider this molecule formed by an oxygen 16 and a calcium 14. At large distance, internuclear distance, they can be identified in the space, and they can be described by two potential wells. And this is up to, in this case, the distance between them is 16 Fermi. But then these two get closer, the shape changes, and the potential that describes the molecule at this internuclear distance is different. And this is changing while the internuclear distance changes and diminishes until they ideally fuse and the distance is 0. And we form the compound nuclear that in this case is nickel 56. And in here we should have one potential well that describes the nickel 56. So you can imagine that, of course, the spectra of these potentials will vary. And this is here. Here we have the energy of the states, of the bound states of these potentials as a function of the distance between the two nuclei. So here, 14 Fermi, you can imagine to project this line up to infinity. It will be straight line, and then this will represent the spectrum of oxygen and calcium together. And this is, yeah, what we can measure and what we can find with any other model. But then the distance reduces here. So this spectrum is changing. So here 7 Fermi, you see, well, it's more or less the same, no? Here it's changing. Then at 4 Fermi is completely different than before, right? And yeah, until we get to 0, and we observe the spectrum of nickel, of the compound nucleus. And we can see the Landau-Zener effect. So this transition between these two states, that's maybe predicted to be this one, for example, at intermediate distance will be much smaller. And you see that a molecular spectrum is already a predictive tool. So I put together the two intuitions, the time-dependent dynamics and the molecular structure. So what I did was to take my semi-classical simple model without angular motion and everything, and added the molecular description, still keeping, of course, the time-dependent dynamics. And here, the new thing with respect to molecular model is that I can describe bound and continuum state in this molecular picture. And this will allow me to simultaneously describe all channels. So let's see how it works. So like together, before, we have the two potential wells, but now we solve the eigenvalue problem for them together, not independently. So we get some bound states, some continuum. This is obvious because we solve this, the Schrödinger equation. And of course, I need to discretize it because I need to use a computer for describing this model. So yes, we will have some bound state and some continuum discretized states. The point is that the distance between these two is changing during time. So we will need to define a basis for each internuclear distance. So in this sense, we have a time-dependent basis. Yeah, there will be, this case will be different than this one and this one. Bound states will look like this. At large distance, we have this solution, for example. And now if we decide to take just this potential well and solve the eigenvalue problem for this potential well, we will get exactly these two states, the same with this other one. But then when they get together, you see here this weakly bound state has a different tail. So compare the tail here and the tail now at reduced distance. So this is changing. And continuum states look something like this. So in one center situation, yeah, like what we had before, continuum were oscillating waves with a phase shift induced by the well we were considering. So for the target, we would have something like that. For the projectile, we would have something like that. So this wave are blind to the presence of the other nucleus in this space. With a two-center continuum, with a two-center model, we have a phase shift induced by both nuclei. And of course, these are changing because the distance between the two nuclei is changing. Yes, so let's run a time-dependent model. Yes, we can, like before, we can run the total wave function time evolution, or we can run time evolution considering the coefficients this function on this molecular basis. And by comparing the two, we can validate our molecular model. And this is done here. So here we have the elastic transfer and breakup probabilities as a function of time. And yeah, the dashed line is the solution of the total wave function evolution, and the solid line is our two-center result. So we see that they compare quite well. But what is more important is that the total probability in the case of the two-center model is conserved and it's stable during the entire reaction up to 10 to the minus 5. So we can look at what happens during the reaction, and we can imagine that's physical what the problem is providing. So let's do that. Let's observe a narrower time window around the turning point. So here we have the same case as before with elastic transfer and breakup probabilities as a function of time. We also have here the internuclear distance. This is a semi-classical model, so the distance and time are related, so we can plot them together in this way. So here we have some energy for this reaction, and here I've used 1 order of magnitude more. You may think this is not available in an experiment, but this is a qualitative theoretical model. We can do what we want, right? So I can use this energy. Okay, so what happens for the in the case we have the lower energy? So around the turning point, you see that there are this variation in elastic and transfer probabilities. And I interpret it as the probability to find a neutron orbiting around this molecule. And it is shared between the target and the core. But then when they get away, it is more probable to find the neutron still bound to the core. And it's practically not probable to find it in a transfer channel. And there is some breakup probability. Let's increase energy. Here things happen faster. There's no more this orbiting situation. Instead, it is more clear that it's almost 50%, let's say, probable that the neutron is transferred directly to the other potential, and the other 50, about 50% probability to find it still bound in an elastic situation. And the breakup probability has increased. So yes, we can look with this time-dependent and molecular model, we can look at what happens during the reaction and what's the interplay of these channels. Now I am extending this model to three-dimensional space. So I have angles, and I'm using a full quantum dynamics description. So I will no longer have this fixed trajectory. Now the motion is driven by the interaction between the two nuclei. And yes, I am concentrating on the collision of one neutron or one proton nuclei on heavy targets. And yes, with this 3D space, 3D extension and full quantum dynamics, we will be able to validate the model against data to evaluate the effect of angular motion, because of course we have angles, we can check it. But then it is full quantum dynamics, so we have introduced fusion, and we can be able to see how fusion competes with other channels, like transfer, like in the measurements we observed, but also with breakup, because we have a continuum here, a molecular continuum. And yes, so we can start with this study of fusion in competition with the other direct reaction channels, but then we can do exciting things like adding 1 neutron more. So let's see, we can see what happens with the 2 neutron helinuclei or spin nuclei if we add more neutrons, and see what how pairing affect this the reaction. We can deform cores or let the cores excite. And yeah, also I'm using phenomenological potential because it's easier for starting, but then it would be really interesting to use mean field theory results for them, of course. And also, why not? We can add external fields like lasers and plasma. This is something we are already studying in Surrey in simpler models. Lasers and plasma are time-dependent fields, so a time-dependent model is perfect for studying them. But imagine to add these fields to this model in which we have all channels, so the direct reaction and fusion channels. We can tune the feature of lasers to see if they can enhance one particular channel above the others. So yeah, we can, there's the potential for a lot of exciting things here. Yeah, okay, so we got to the conclusions. I have shown you this model that is based on time-dependent dynamics and a molecular structure. And I have shown you in a simple reaction model with a Wicklieband projector the potentiality to study simultaneously all channels. And yes, let's be optimistic and think that this will provide us a predictive tool for experiments, and that will allow to explore reactions in a new way, and yeah, hopefully pushing forward our understanding of nuclear reactions. And thank you.
Any questions from the audience here? Yeah, please go ahead.
Well, thanks for the very different and interesting talk. So I was interested in how your TCCE, I guess, time-dependent channel equation and time-dependent Schrodinger equation, that they were similar at asymptotic times, but in intermediate times there was a difference.
Yeah.
So can I understand that in that the approximation you're making is you're cutting off high energy states from your Hilbert space. And so that truncation does not actually change the S matrix. It doesn't change the cross sections, but it does change the dynamic at intermediate times.
Yeah, maybe, yes, we can play with how many states we include up to which energy, and yes, and see an improvement. Actually, this is, yeah, this difference is 2%, but still it's there, of course. And yeah, but the beauty of this is that the Hilbert space of the molecular basis spans all the region of the collision. So we can yeah, the region on which the two nuclei move is described by the basis at any time.
My question goes in the same line as Steve, because it looks super cool. I just want to understand better how you can improve it if I want to get a perfect match. Mm-hmm. So can you go to your slide? You have a very pretty slide. Well, we have many pretty slides, but you didn't have numbers. So I don't know. The one where you had the nickel, oxygen plus calcium, you were showing the difference. Yeah. So if I understand correctly, in the other side, you have your estimation for the wave function. as a linear superposition of wave functions that depend on this R of time. And you have fixed your trajectory. So what happens at each time is that you grab that spectrum that you have on the right for your particular problem, and you say, this is my basis is made out of all the wave functions that I can make out of this.
Yeah.
And then the only dynamics that you're having is how do my coefficients C change in time?
Exactly.
That is what you're doing.
Yeah.
Right? What are you doing with the true time-dependent Schrodinger equation? You don't have that approximation.
No.
How do you solve it?
No, I just take the initial state. It's exactly the same I shown you here. I just take the initial state and put it. Yeah, well, okay. Just take this state, put it in this equation, and run with an operator with a
Exactly, but then the target and projectile potential wells are still fixed on the same time-dependent trajectory.
Yes.
You're not changing, you're not impacting the trajectory.
No, exactly, it's the same trajectory.
Okay.
Exactly the same.
So yeah, I'm studying the same thing of being trying to understand what could you do to your model to make the overlap perfect?
Yeah, okay. I think it's the range of the continuum, the energy threshold in the continuum. Yes, I think that's where we can play with that better. Yes.
I will know you more later when I meet with you.
Yes, sure.
So, perhaps I can make a comment. I just wanted to comment on it. No, we're not trying to match those two. I don't think there is the intent of matching those two. The differences between those two just tell you the effects of the molecular dynamics. So you're not ultimately going to have TDSE match the couple channel version, because this is what's missing in your model, is when you assume that these two molecular configurations are not being distorted when they approach each other, that's what you get.
Yeah,
you don't get the same business, you get something different.
But in this picture, she's not changing the configuration of these two wells either. They are not influencing each other, right?
Well, they are solution of the molecular dynamics, right?
I think we can, so I expect to see a difference respect, for example, in using the 3D model, running, for example, Fresco calculation for, to get some transfer cross-section. I would expect to have a different transfer cross-section with my molecular model. So to those.
Sorry, it was just a
No, thank you.
Yeah. No, but it's in this.
Yeah, Peter first and
sure. You discretize the continuum that you show us, but continuum as a structure. So there appear resonances, for instance. So how do you deal with those?
Yeah, so with this, in this model for the semi-classical, I discretize the continuum with a box. So it's difficult to see resonances in that way. We should use, like transformed harmonic oscillator. If I want to diagonalize to see, there are methods to see resonances. In the 3D model, I expect to see resonances because yes, I'm using harmonic oscillator basis to diagonalize. And that way I can get resonances. But that it's interesting because, for example, let me check here. That's easier to show you. So here we have bound states, but then, of course, continuum spectrum. We provide us some other lines here at positive energies. And what is a resonance at large distance may not be a resonance anymore at intermediate distance, and a new resonance may show up at another distance. So that's interesting actually to see the evolution of this. Also, a very weakly bound state at intermediate distance may end up to positive energy during the reaction. So and then come back to be bound at the end. So that's interesting to see the effect
You mentioned harmonic oscillator, but it's not typical harmonic oscillator.
No, but we can use the transformation.
Transfer. What was
Transform the.
Transform harmonic oscillator.
Oh, just the technique. Yeah.
Yes, so I want to understand your approach related to time-dependent Hartree-Fock. Is your approach an approximation to time-dependent Hartree-Fock?
Well,
or does it go beyond it in particular directions?
Well, we don't have excitation for the cores in this model, so they are not related at the moment. But so
you're not self-consistent, for example.
No.
But is that the only difference?
Yeah, I think so. Yeah.
I think you should mention in the last slide that there's some kind of ETL theory can be used to describe the two core dynamics. So in some sense, complicated.
Yeah.
You're adding more neutrons on top of this.
Yeah, it's another idea. Also, allowing the core to excite. So that probably will bring to closer to the.
Yeah, following that line, like you didn't mention impact parameter. So in some sense, the core dynamics differ a lot. I mean, depend a lot on that parameter, right?
Yeah,
it does. Far apart when that glows head on. So do you think your framework here will work for both extreme situations or actually?
Well, the 3D one, yes, yeah. Because it includes angular momentum, so we can talk about impact parameters.
So if the impact parameter is small, like when the two cores really get close to each other and have all these compound dynamics, they have a neutron flying away.
In 1D, it's always B is always 0.
Right, I agree, but
yeah,
I'm looking to
we don't have that problem.
I'm getting to the 3D case, like we're talking about impact parameters. Well, in the central collisions, you really have very complicated core dynamics. So how do you?
Well, yeah, okay. I just keep inert the core and I just see what happens to the neutron. So yeah, I may jump to another state and yeah.
Okay. Yeah, this is actually that following the line of time-dependent Hartree-Fock. Yeah.
Yeah, maybe we can discuss about it.
Yeah, go ahead.
Okay, second one last one. So maybe I missed something, but how your initial relative kinetics will influence the channel, the probability of different channels.
Well, so you mean the energy of the collision?
Yes.
So if well, yeah, okay. So when it is about the Coulomb barrier, we can expect to observe an interplay between channels. When it is very different than this Coulomb barrier energy, we can expect to find clearly one channel dominant with respect to the other, or when it is really smaller than the Coulomb barrier.
So this relative kinetic energy is already in your
Yes, it's an input value. Yeah.
Any more questions?
So it's sort of a provocative question, but it's very nice to work in 1D because you can run it in your laptop and you get all the intuition. But of course, nuclei aren't like that, and we need the full 3D. And so the question is, I've seen a lot of toy models in 1D that with the intention of being ported to 3D that eventually didn't, people just dropped it after a while because they realized it became a lot more complicated.
Yeah.
So the question to you is really, as you're doing this, because I know it's in progress and you've already made some strides in that direction. As you're doing this, what have become the major complications, and how computationally heavy do you expect this to ultimately become?
Well, the complication is the computing time. Of course, it's increasing. The calculation is heavier. For now, I'm testing the L = 0 case. and I'm just including few states, just 2 or 3 states, and it takes some hours, like 4 hours, which is manageable now. But what I want is to include more states, to include a dense mesh, so that will increase the computational time. But I think it's feasible to go to a cluster, and it will be feasible to calculate the full model there.
But if you've got these deformed structures that are coming together, then you're going to mix angular momentum as well, right? So
yeah, exactly.
So
that will be interesting. Yes, that will require cluster. Yeah, 100%. Yeah.
Just following the last question, is there any similar development in quantum chemistry in other fields?
Well, there are molecules, but they are not used continuous things. So
time dependent.
Yeah, there are examples of these. Yes.
Yeah. So in terms of complexity, I think.
Yeah, the same.
Whether they have made any progress.
Can you use existing time-dependent Hartree-Fock codes, for example, the 3D grids that they work on?
No, because I don't have the two-center description.
So, we have a lot of people get interested in time-dependent Hartree-Fock.
Yeah, so we can maybe discuss and see if there's something common there. But the difference I see is the two-center description. That's something. Yeah.
Seems like we don't have budget from online, so let's just close it. Thanks, Peter.